Hello, welcome to another module in this massive open online course. So, we are looking at example problems for convex functions. Let us continue our discussion. All right, we are looking at example problems, and let us look at problem number 8. And we want to consider the function norm x bar square by t, which you can also write as, remember, norm of vector square is vector transpose times itself, that is x bar transpose x bar divided by t. You can think of this as an n plus 1 dimensional function. So, we have, if you define the vector x tilde equals, well, the vector x bar t augmented with t, which is basically, you think of this as x1, x2 up to xn and then one additional element. So, this is basically your n plus 1 dimensional vector. Okay, this is an n plus 1 dimensional vector. We have this function f of x tilde. Okay, so this is x tilde is the vector x bar that is augmented with t, and we can consider further that t is greater than 0, that is t is a positive quantity. Okay. Now, we want to show that this function is indeed a convex function. Okay. We will follow the approach that we have shown before, that is the test for convexity, which is to evaluate the Hessian and demonstrate that it is indeed a positive semi-definite matrix. Okay. So, what we want to do is we want to evaluate the Hessian of this. First, let us start with the gradient with respect to x tilde of f of x tilde, which will contain first all the partials with respect to all the x's, followed of course by the partial with respect to t. Okay. And well, if you look at this, well, you can simplify this x bar transpose x bar. So, f of x tilde norm x bar square by t, which is also x1 square plus x2 square plus xn square divided by t. You can see the partial with respect to x1 is simply 2x1 divided by t, partial with respect to x2 is 2x2 divided by t, partial with respect to xn is 2xn divided by t, and the partial with respect to t is norm of x bar square into, differentiate this with respect to 3. So, that will give us minus 1 over t square. Okay. So, the partial with respect to t is minus norm x bar square divided by t square. So, this is your partial with respect to, partial derivative with respect to t. Okay. And now we have to compute the Hessian for this. Okay. This is basically the gradient, we have to compute the Hessian. Okay. And that is also, it has an interesting structure, it is fairly straightforward, you just have to pay attention to each element. Now, first, well, the 1 cross 1 element is the partial with respect to x1, that is the second order partial with respect to x1 square. So, you take 2x1 over t, divide it with respect, differentiate it with respect to x1. So, that gives you 2 over t. Now you take 2x1 over t, differentiate with respect to x2, that gives you 0, differentiate with respect to x3 0, in fact differentiate it with respect to, now the last element will be the derivative, that is 1 comma n plus 1th element will be the derivative with respect to t, and that will be minus 2x1 over t square. Similarly, you have all these elements are 0 and the last element will be again minus 2 x1 over t square. Now look at the 2 cross 2 element, that is the derivative partial, second order partial with respect to x2. So, you take 2 x2 over t, differentiate with respect to x2, that is 2 over t. Of course, rest of the elements will be 0 and this last element will be once again minus 2 x2 over t square. This element here will be minus 2 x2 over t square. You will have so on and so forth, and here the last element here will be partial with respect to second order partial with respect to t. So, this will be minus norm x bar square derivative of 1 over t square, that is 2 over or minus 2 over t cube. So, that will be 2 over t cube. This is basically the Hessian. Okay. So, you can see this is basically, you can see each element. So, this is basically the 1 cross 1 element, this is basically the 2 cross 2 element, this is your 1, I am sorry, I should say 1 comma 1 element, 1 comma 1 element, this is the 2 comma 2 element, that is the diagonal element, this is your 1 comma n plus 1 element, and so on. Okay. And this last element here, this is your n plus 1 comma n plus 1 element. Okay. So, this is a Hessian, it has an interesting structure. So, the first n diagonal elements are all 2 over t, the last n plus 1 comma n plus 1th element is 2 norm x bar square divided by t cube, and along the last row and the last column you have the elements which are of the form, entries of the form minus 2 xi over t square. So, that is the structure of the Hessian. And now you can divide this into the sum of several matrices, each matrix with respect to one of the xi's. So, the first matrix will be with respect to x1. So, you can take this and this has the particular structure. So, this will be 2 over t, last element will be minus 2 x1 over t square, 0 0 minus 2 x1 over t square, and the last element out of the norm x bar square you simply take x1 square. So, this will be 2 x1 square divided by t cube. Okay. So, this you can think of this as a corresponding to with respect to x1 or corresponding to the x1. Similarly, corresponding to x2 you will have a matrix which is of the form 2 cross 2 element is 2 over t, the last element is minus 2 x2, last element in the second row is minus 2 x2 over t square, this is 0 n plus 1 comma 2, the last the second element in the last row, that is again minus 2 x2 over t square, and again you take n plus 1 comma n plus 1th element, you take the component corresponding to x2. So, this will be 2 x2 square over t cube plus so on. So, total of n, you have a total of n such matrices. Okay. Well, for the ith matrix you will have, if you look at the structure of the ith matrix, okay, the ith matrix corresponding to xi will have 2 over t in the I comma ith element. This will be minus 2 xi over t square, this is n plus 1 comma I. Similarly, here you will have minus 2 xi over t square, and the n plus 1 comma n plus 1 element, that will be 2 xi square divided by t cube, and the rest of all okay. So, this is the matrix, you can think of this as the ith matrix. This is basically your I comma n plus 1th element, this is your I comma ith element, this is your n plus 1 comma ith element, and this is your n plus 1 comma n plus 1th element. Okay. So, this is the structure. Okay. You can decompose it into such matrices. Okay. And now, so I can write it as the summation. So, I can write this or rather let us now I can write this as the summation over I of such matrices. I equals 1 to n, you have minus 2 xi over t square minus 2 xi over t square and 2 xi square over t cube. Okay. And the rest, all the rest of the entries are zeros. Okay. And now if I take 1 over, that is 2 over t cube as common, so I can write this as I equals 1 to n, take 2 over t cube as common, this will become again very simple. So, if you take 2 over t cube common, this will be t square, this will be minus 2 xi times t minus 2 xi times t, and this will be well, this will simply be, I am sorry, the 2 will go because we have taken the 2 outside. So, minus xi t, and this will be simply xi square, and rest of the entries are 0. Okay, rest of the entries are 0. And now you can see I can decompose this as I equal to 1 to n 2 over t cube. I can write this as 0 0, then you have a t in the ith position minus xi in the n minus n plus 1th position times 0 0 t, again you have zeros, and minus xi in the nth position. So, this t is in the ith position, this minus xi is in the n plus 1th position. And now you can see I am writing this, basically decomposing this as ai bar transpose. Okay. So, ai bar is this vector, ai bar is basically your vector which has t in the ith position and minus xi in the in the n plus 1th position, and therefore, I can write this as summation I equals 1 to t 2 over t cube ai bar transpose. Now, each of this is a positive semi-definite matrix. Remember, whenever a matrix can be decomposed as A transpose, correct, it is a positive semi-definite matrix, that is what we have seen. You are weighing it by a positive coefficient, because remember t is greater than 0, so 2 over t cube is greater than 0. So, sum of positive semi-definite matrices weighted by positive coefficients, the resultant matrix is also positive semi-definite. Therefore, the Hessian is positive semi-definite and hence the function is convex. Okay. So, this is greater than 0 implies the weighted sum of PSD matrices is PSD, which implies that the Hessian f of x tilde equals is a PSD matrix, which implies f of x tilde is indeed a convex function. Alright, so that is that is what it's a slightly involved and lengthy proof, but as we have seen, some of these tend to be a bit involved. Okay, so we have demonstrated that norm x bar square divided by t, that is x bar transpose x bar divided by t, considering this as a function of the n plus 1 dimensional vector x bar augmented with t, this is a convex function. Okay. Let us proceed to the next problem, that is problem number 9. Given two functions f of x, g of x, which are convex, and these are greater than 0, that is f of x comma g of x greater than 0, and further these are non-decreasing. We want to show that h of x equals f of x into g of x is also a convex function. Okay. And that is easy to show. So, we consider first the first order derivative of h of x, which we denote by h prime of x using the product rule, that is f prime of x g of x plus g prime of x into f of x. Now, considering the second order derivative, it is h double prime of x, which is f prime of f double prime of x g of x plus f prime of x g prime of x plus well g double prime of x f, I am sorry, this has to be g prime of x into f x, g double prime of x f x plus g prime of x into f prime of x, which you can now simplify as follows. You can write this as this is equal to, well, f double prime of x g of x plus twice, you can combine these two terms. So, that gives you twice f prime of x g prime of x plus g double prime of x f of x. Now, let us dissect this term by term. If you look at this quantity here, you can see f of x is convex. Okay. So, this implies f double prime of x is greater than or equal to 0. Now, g of x is given to be greater than or equal to 0 or greater than 0. So, this implies f double prime of x into g of x is greater than or equal to 0. Now, f of x and g of x are non-decreasing, This implies f prime of x comma g prime of x greater than or equal to 0. This implies the product, that is, since they are non-decreasing, both of them are non-negative. So, the product is also non-negative. And now, the last term is similar, g is convex. This implies g double prime of x is greater than or equal to 0 given f of x greater than 0. So, this implies g double prime x into f of x greater than or equal to 0. So, all the three components in the sum are non-negative, therefore, the sum is non-negative, which implies the second order derivative h double prime x is non-negative, or it is basically greater than or equal to 0, which implies essentially that h of x is convex, or the product f of x into g of x is convex. So, this implies h prime of x greater than or equal to 0, this implies h of x is convex, which is nothing but f of x into g of x. This implies that f of x into g of x is convex. Let us now move on to another problem, problem number 10. Now, consider a set of variables x1, x2, xn, or a vector, or let us say we have x bar, this is an n dimensional vector, okay, and we have xj is the jth largest of x1, x1, x2 up to xn, okay, which implies that basically you are sorting this. So, what this means is the largest is x1, which is greater than, if you sort these, x2 is greater than or equal to x n, n with the square bracket. Remember, this is actually different from xn. So, x1 x square bracket or x subscript bracket, you can say x subscript square bracket 1, this is the maximum or the largest, and this is the largest, and this is the minimum, okay, and x subscript square bracket j, that is the j largest, jth largest, that is, if you arrange them in descending order, x subscript square bracket 1 is the largest, followed by x subscript square brackets 2 and so on, okay. And let us assume the non-negative coefficients alpha 1, which are again arranged in decreasing order, such that alpha 1 greater than alpha 2 greater than alpha r greater than or equal to 0. Now, what we want to show that this function of x bar, which is alpha 1 x 1 plus alpha r x r, we want to show that this is convex, and this can be seen as follows. Now, this is an interesting function. First, you can see what you are doing is you are taking the r largest, alright. This is very interesting and very complicated function. So, you are taking r largest plus you are taking the linear combination. And this is a highly nonlinear function, because when you look at the maximum of the maximum is basically a nonlinear function, correct. So, we are taking the r largest and you are taking a nonlinear, you are taking a linear combination. So, this is basically it is a highly nonlinear function, because although you are taking a linear combination, you are looking at the maximum of these elements, right. So, this is a highly nonlinear interesting function, yet you can demonstrate that this function is convex, and that can be done as follows. In fact, it is very simple. If you consider the function f I of x bar, which is defined as alpha 1 x I 1 plus alpha 2 x I 2 index I 2 plus alpha r x I r, where I 1 I r, these belong to the set 1 to up to n, and none of these two are equal, or no two of these are equal. All of them are distinct, no two are equal. So, which implies I 1 I 2 up to I r are distinct. Now, how many ways can you choose these indices I 1 I 2 I r? In fact, I can call this as f of, let us say, some index, not I, because we are using f of, let us say, m, okay, just one particular combination. So, basically it depends on total number of, not even combinations, because remember, for alpha 1 you have to choose one index I 1, alpha 2 you have to choose one index I 2, and so on. So, you have to, this is basically a problem of permutations, how many ways, that is basically you are choosing the ordered pairs I 1 I 2 up to I r. So, this is basically the permutation. And what is the total number of such, you want to ask the questions, what is the total number of such functions? What is the total number of such functions? That is the total number of permutations of r objects from a set of n objects, that is n p r. So, total number of permutations will be n p r. You might have seen this in high school, this is n factorial by n minus r factorial. Okay. So, that is the total number of such functions f, total number of such functions f m of x bar. Now, you can see that each of these is a hyperplane, each of these is a that is f m of x bar equals alpha 1 x I 1 plus alpha r x I r. Each of these, very interestingly, this is a which implies this is convex. So, each of these functions is a hyperplane. Okay? Each of these functions corresponding to a permutation of this r x r variables x I 1, x I 2, x I r, this is a hyperplane. So, each such function is convex. And now therefore, if I take the maximum of this, for all the, you take the maximum of this for each x bar for all the m less than npr, that is you take the maximum of all these npr or n factorial by n minus r factorial functions, you can see that the maximum is nothing but alpha 1 times x of x subscript square bracket 1 alpha 2 x subscript square bracket 2 plus so on alpha r x subscript square bracket 1. That is, a maximum occurs. Remember, we have said these coefficients alphas are arranged in the decreasing order. So, alpha 1 is greater than equal to alpha 2 is greater than equal to alpha 3 greater than equal to so on up to alpha r. So, maximum occurs when the maximum alpha 1 is associated with the largest. So, this is the largest alpha, this is the maximum xi, this is the second largest and second largest alpha I, this is the second largest xi and so on. Therefore, the maximum is nothing but alpha 1 x subscript square bracket 1 so on summation alpha r x subscript square bracket r, and this is nothing but our f of x bar. Now, you can see that f of x bar is the maximum of a set of, in fact this is pointwise maximum, that is for each x you are taking the pointwise maximum of a set of NPR convex functions, in fact hyperplanes. Implies that f of x bar is convex. Alright. So, basically you are taking NPR, that is n factorial by n minus r factorial convex functions or hyperplanes, and you are taking the maximum, the pointwise maximum of these NPR hyperplanes, and therefore, the resulting function is also indeed convex, and that basically completes the proof for this interesting problem. Alright. So, we will stop here, and starting from the next module we will start looking at various convex optimization problems, their practical applications in various domains. Thank you very much.